Alright, so in this section we're going to talk about some reaction types. So firstly we'll talk about double displacement, gas forming, and then lastly acid-base neutralization, and then finally we'll end with some combustion reactions. First we'll start with double displacement, also known as metathesis reaction, also known as a precipitation reaction. Double displacement is exactly what it sounds like. So it means that we're displacing two things. So in our example here, we have AB plus CD giving us CB and AD. So what's happening there? So C and A are swapping places. Okay, so hence the name double displacement. So we're displacing two different things. C is displacing A and A is displacing C. The next one is gas forming reaction. So this is often seen with metals and acids. So here we have something like either magnesium or zinc put into an acid solution, and you see there's lots of little bubbles forming. Okay? In other words, that's where it gets the name gas forming. At the bottom, we have acid-base neutralization. So if we have a base combining with an acid, so here we have sodium hydroxide combining with HCl to give us H2O and NaCl. Okay, so why do we call it neutralization? Well, because what we end up with is water and a salt. Okay, so in other words, we don't have any acid or base left. So we've neutralized both the acid and the base. And so let's dig into each of these a little bit deeper. So firstly, let's talk about what do we need for a reaction to actually occur. So it has to be favored both kinetically and thermodynamically. So with the kinetics and thermodynamics conditions met, then we have to have driving forces. So what do I mean by the kinetics and thermodynamics? So it means it has to be energetically favored, okay, in terms of thermodynamics, and it also has enough energy in terms of kinetics. So in other words, the molecules have to meet, they have to meet with enough energy, etc. So it has to be both kinetically and thermodynamically favored. And then once those are met, then we have to have a driving force. So the second statement says, with the kinetics and thermodynamics conditions met, the driving forces behind the chemical reactions are. So these are very important. I'm going to put a big emphasis on this because these are important. So in order to have a chemical reaction, you have to have one of these driving forces. If there's not a driving force, then there's no reaction. So what are the driving forces? Well, it can be the formation of a gas, it can be making a liquid, the formation of a precipitate, in other words, a solid, or it could be the exchange of electrons. So we make a gas, we make a liquid, we make a precipitate or a solid, and we exchange electrons. Now, we don't have to have all of these, but we have to have at least one. If at least one of these does not occur, then we don't have a reaction. At the bottom it says at least one of the four driving forces must be observed for a chemical reaction to have occurred. Yeah, so if I don't see a gas, if I don't form a pure liquid such as water, if I don't form a solid precipitate, or if I don't exchange any electrons, then nothing's happening. I'm just putting chemicals together and nothing's really happening. Okay, so I have to have one of these driving forces for a reaction to have occurred. Okay, so let's look at a couple reactions here. So two main categories. So I have decomposition and I have synthesis. Okay, so in a decomposition reaction, it means that one reactant decomposes into two or more products. Okay, in other words, I start from one thing, maybe that thing is not very stable at room temperature or something like that, and it breaks down into at least two or more things. And I have synthesis. So here in a synthesis reaction, I have two or more reactants combining to make a product or products. So it could go from two things to one thing, or it could go from two things to many things. Okay, so that would be synthesis. So decomposition, we start from one thing, turned into many things. Synthesis, we start from at least two things, we form one or more products. Okay, within synthesis reactions, we have basically those things we talked about before. So double displacement, also single displacement is possible, reduction, oxidation, and neutralization. So with a double displacement, what I showed you before is still true. So we have two things displacing each other. In other words, they're just swapping places. So I have two ionic compounds, and perhaps their cations are switching places, or you could look at it as their anions are switching places. Both would get you the same thing. Okay, so that's double displacement. And very similarly, single displacement, I have one thing displacing another. So instead of having two ion switching places, I have basically one ion displacing another. Okay, so double displacements, often we see them as precipitation reactions. And for single displacement, often these are your gas-forming reactions. Okay, and below that I have your decomposition. Okay, so that's one thing becoming two things, as you see. Combination or synthesis, I have two things becoming one thing. They could also become more than one thing. And next I have reduction oxidation. So this would be example of combustion reactions or corrosion reactions. We'll look at those closer in a moment. And then we have neutralization reactions. So this is a reaction between an acid and a base. Okay, so double displacement. So here we have the exchange of ions. In other words, the switching of partners between reactants to form products. So here I have AX plus BY giving us AY and BX. So here they're exchanging the X and the Y. So if I want to write out a double displacement, the first step, obviously I have to know my reactants. But the next step is to determine the formulas of the possible products. So the positive ion from one reactant and the negative ion from the other. Basically you're adding those together. And then you want to balance the charges of the combined ions to get the formula of each product. So basically, switch the partners and then write the appropriate formula. So if I have, for instance, potassium combining with chloride, well then I just have one potassium and one chloride. But if I have, maybe calcium combined with chloride, well then I have to have two calcium. So that's what they're trying to say here. So make sure you balance the charges. So switch the partners to make new ionic compounds and then balance the charges. Number 2, determine the solubility of each product in water. So you want to use your solubility rules. And if the product is insoluble or slightly soluble, that will be precipitate, in other words, a solid. And if neither will precipitate, there's no reaction, an equation cannot be written. So you would write something like this. You could write NR like that. That's the way it's commonly done. So that's if, number 2, what I'm saying is, if you don't find an insoluble product. So if everything's soluble, well then all you have is just a solution full of ions. So nothing's actually happening. Okay, so reactions between aqueous solutions of ionic compounds that produce an ionic compound that is insoluble in water are called precipitation reactions. And the insoluble product is called a precipitate. Okay, so the solid that's formed from a precipitation reaction is a precipitate. And so the driving force is the formation of the insoluble compound. So the precipitate is our driving force. Again, without that, all I have is solution. So if I have, say, a positive ion plus a negative ion plus, positive ion plus a negative ion gives me positive plus negative, etc., well, then I haven't actually formed anything. So I have to have something that's insoluble to actually form my reaction, and that's my driving force. Okay, so your solubility rules are used to determine whether or not the products that form are insoluble or not, of course. So as an example here, I have barium chloride reacting with sodium sulfate to give me barium sulfate and sodium chloride. Okay, so I'm going to swap sodium and barium, or you could do it the other way around. Okay, and I'm going to end up with barium sulfate, sodium chloride, and again, I have to balance all my charges. No big deal there. And then I want to use my solubility rules to figure out if I have an insoluble product. I do, barium sulfate, that's my insoluble product. So therefore a reaction has occurred. So let's take a look at how this would actually be used in the lab. Okay, so here maybe I'm trying to remove the iodine from the solution, or remove the iodide from the solution. So I have two solutions reacting. So I have potassium iodide reacting with lead nitrate to give me potassium nitrate and lead iodide. So what I want to do is when I combine these two, notice that my lead iodide is insoluble and therefore becomes a solid. That's my driving force. And now below we have a description. So when potassium iodide solution is mixed with lead-2 nitrate solution, a yellow lead-2 iodide precipitate forms. So let's take a look at what's actually happening. So in our top solution, we have potassium iodide. So swimming around in this solution, we have potassium ions, we have iodide ions, some K plus and I minus. And that's perfectly happy to be in solution as long as it's not combined with anything else. Okay, and then in the bottom solution, we have lead and we have nitrate. So we have lead plus or lead 2 plus and nitrate minus 1. And again, those are happy to be in solution. As long as there's nothing else around, they're perfectly happy. But once we combine the two, so once we pour this solution into the other, notice what ends up happening. So we end up forming this yellow cloud of solid. Okay, so what's happening there is exactly what the reaction says. Okay, so all of our some of our ions are still just swimming around, but the ones that are insoluble, or in other words, the ones that form the insoluble compound, those are forming a solid. Okay, in the lab, we call this crashing out, or in other words, the formation of a precipitate. So notice we still have potassium ions left over, and we still have nitrate ions left over. So the only thing involved is really the lead and the iodide. Okay, so that's how we know a reaction is occurring. And then we have our reaction down below. But that's how we know a reaction is occurring. If this was if this wasn't here and we just still had lead and iodine floating around, well, that wouldn't be any different than having the solutions apart, except that they're mixed. Okay, but since we do form an insoluble compound, we have a reaction. Okay, so let's go through an example. So it says, write the equation for the precipitation reaction between an aqueous solution of potassium carbonate and an aqueous solution of nickel 2 chloride. Okay, so one thing we have to know is we have to know how to write these compounds. If they're not given to us, we have to know how to write them. Okay, so firstly it says write the formulas for each of the reactants. Okay, so we'll just write potassium carbonate plus nickel 2 chloride. Next it says determine the possible products. So it's determine the ions present, exchange the ions, and then write the formulas of the products. So take the ions, swap partners, write the new products. If both products are soluble, then you would write no reaction, or you could put an X over the reaction arrow. Write aqueous next to the soluble products, and write solid, so an S, next to the insoluble products. So AQ is your symbol for aqueous, and S, of course, is your symbol for solid. Okay, and then balance the equation. Okay, so here's an example. So let's write the equation for the precipitation reaction between an aqueous solution, potassium carbonate, and an aqueous solution of nickel 2 chloride. So this is the example we're just working with. Okay, so I'm going to work this one out with you. Okay, so let's take a look at this one. So the first thing we want to do is we just want to write out our reactants. So step one, let's write out our reactants. Okay, so I have potassium carbonate, which is K2CO3. Remember that carbonate is 2 minus, plus an aqueous solution of nickel 2 chloride, so NiCl2. Okay, so that's our first step. And I can write a reaction measure, arrow just for good measure. Okay, the next thing we need to do is determine our possible products. So I'm just going to rewrite the reaction over again. Okay, so I have K2CO3 plus NiCl2. And you don't have to keep rewriting it like this. I'm mostly doing this for demonstration. And I'm going to switch colors so you can see what I'm adding new to it. So now I'm going to predict my products. So I'm going to switch potassium and nickel. So what I end up with let's keep the anions where they are. We end up with Ni. So we know it's already nickel chloride, nickel 2 chloride, so I can just write NiCO3. And my second product, now I'm just swapping potassium and nickel to give me KCl. Okay, so that's my second step, just determine my possible products. Okay, then number 3, I'll grab purple again. So number 3, now I want to determine the solubility. To see if I actually have a reaction. Okay, so let me look at my products. So I have nickel carbonate, and I have potassium chloride. Well, I know potassium chloride is going to be soluble, so I have a group 1 there, and a halogen. Okay, so go ahead and write out AQ for aqueous. Okay, and then nickel chloride. This is one where I would have to think about it, because maybe I'm not sure. I have to go back to my solubility tables and really figure it out. I happen to know this one's insoluble. Okay, so once I have my states written, that's really the last step. So now in the typed out example, they give you a few more steps, whereas you sort of break everything into ions first. I'm just going with the direct method at first. So let's stick with this for now, and let's jump back over to the slides, and I will show you kind of what I mean here. Let me go back a little bit. Okay, so here they gave you the first step, write the formulas, then determine possible products. So here, this is what I was saying. They break everything to ions first, and this is a great thing to do. So write K plus CO3 2 minus plus nickel 2 chloride, or nickel 2 and the chloride. Okay, then exchange the ions, and then put everything back together. Okay, so I did this all just kind of in one step, and that's the way you're going to end up doing it eventually. But this is a good way to sort of step by step to do it. Okay, number 3, determine the solubility. We said that KCl is soluble. We said that nickel carbonate is insoluble. Okay, if both products are soluble, write no reaction. Since we don't have a driving force, that would be no reaction. But in this reaction, we do have a solid product. Okay, so we do have a driving force, so we have a reaction. And then lastly, just rewrite the equation, including your states. Okay, then once you have that written, you will balance the equation. So I didn't do this step. Notice here they had to add a 2 here to get everything balanced. So I sort of skipped over that, but that is something you need to do. So this 2 here. And why is that? That's because I have 2 potassium here and 2 chlorides here. So do make sure you do that. Matter of fact, while we're sitting here, I am going to go back to my sample here and go ahead and add the 2 so that when you look at it, you're not confused. Okay, so here's a couple more examples. Give these a try. So see if you can exchange the ions, determine the solubility of the new products, and write the complete equations. So go ahead and pause the video, give these 2 a try, and then I will go over the answers with you in just a moment. Okay, so let's take a look at these. So the first one, we have potassium chloride reacting with silver nitrate. And number 2, we have sodium sulfide reacting with calcium chloride. Okay, I'm just going to go through these with the text. But if you do have any trouble with these, please do let me know. But I feel like it's pretty straightforward now that you've seen one done the long way. Okay, so potassium chloride, silver nitrate. First thing, let's just break them into ions. So we know that it's going to be K plus, Cl minus, Ag plus, and O3 minus. Okay, next we need to predict their possible products. So swap potassium and swap silver. So we end up with silver plus chloride plus potassium plus nitrate. Recombine our ions. Then predict your solubility. Okay, so look at silver chloride and look at potassium nitrate. See if either is insoluble. We know silver chloride is insoluble, so we label that as our solid. That would be the driving force of our reaction. So if I asked you to label the driving force, you could write driving force next to this. Okay. So that one should have been pretty much a dead giveaway. If you see silver chloride, it's insoluble. Okay, next one. So I have sodium sulfide plus calcium chloride. First thing, break my reactants into ions. So I have sodium plus sulfide ion, get plus, calcium 2 plus chloride. Swap partners. So I'm going to swap the, looks like this time they swapped the cations again. Okay, so I end up with calcium plus sulfide plus sodium plus chloride. Now again, I have to check my solubility. So is calcium sulfide soluble? Is sodium chloride soluble? There's no reaction here. And notice again that I have to balance these out. I have to write proper ionic formulas, otherwise it's not correct. But here it says no reaction because sodium sulfide and calcium chloride yield soluble products, calcium sulfide and sodium chloride. So notice these are just 1-in-1 compounds now. But since they're both soluble, no reaction. Okay, so hopefully these are not too tough for you. If you do get stuck with these, please do come see me, send me an email, whatever it is. Okay, so now we're going to talk about net ionic equations. So now that we know how to write double displacement reactions, we know how to write ionic equations, let's talk about the net ionic chemical equation. Okay, so here we have lead nitrate reacting with potassium chromate. They give us lead chromate and potassium nitrate. So the above chemical reaction is written as the complete equation. And so here is because lead nitrate and potassium chromate are strong electrolytes, we could also write this. Okay, so in other words, what have we done? We've broken everything into ions that can be broken into ions. The only thing in this equation that can't be broken into ions is my lead chromate. Everything else can be ionic. Okay? So this is called the complete ionic equation. So the one at the top is the molecular equation or the complete equation. Now this is the complete ionic equation. Why ionic? Because I've broken everything that can be broken into ions into ions. So if I take a look at this, what about potassium and nitrate? So if I look on my product side, I see potassium. If I look at my reactant side, I see potassium. Okay, so I could potentially cancel those out. If I looked on my reactant side, I see nitrate. If I looked on my product side, I see nitrate. So again, I could potentially cancel those out. What am I left with? I'm left with lead plus chromate gives me lead chromate. So everything that's not lead or chromate, these are spectator ions. Why spectator? Well, because they're not actually participating in the reaction. The only thing that they served was to bring the other ions into the solution. In other words, it was just a source for lead and a source for chromate. So I had to have them in some salt, right, before I reacted them. Okay, so that's just their vehicle. That's just the way they arrived in solution. But those ions aren't actually doing anything. The only thing that's reacting is the lead and the chromate. Okay, and we call those spectator ions. So suppose we wanted to write the net ionic equation. We're going to leave those spectator ions out. So all I would do is cancel out, again, cancel out nitrate, nitrate, potassium, potassium. So I'm left with lead plus chromate gives me lead chromate. Okay, so if I write those down, this is my net ionic equation. So let's look at our terms again. So this is the complete equation, or the molecular equation. This is the ionic equation. And if I remove the spectator ions, that's the net ionic equation. Okay, so lead plus chromate giving me lead chromate, that's my net ionic equation. Okay, so here's 4 examples. Give them a try. They want you to write the molecular, complete ionic, net ionic for each of the following. So give these a try, pause the video, and I'll go over the answers with you when we come back. Okay, so let's go at the answers for these. So the first one. So again, we want the molecular, complete ionic, and net ionic equation. Okay, so first we have potassium sulfate reacting with silver nitrate. Okay, so let's see. So we're going to swap our cations. So do the swap there. Okay, so we can predict our products: silver sulfate and potassium nitrate. Okay, so that would be our molecular. Notice here that we have silver sulfate precipitate. Okay, so that would be our molecular. A complete ionic, we would just break everything into ions except for our solid. Okay, and then we have to look for spectator ions. So just real quickly, we have potassium, sulfate. Oh, we can't cross out sulfate, we have to keep it. Can't cross out silver, cross out nitrate, there we go. Okay, now we can write our net ionic by just removing those, keeping everything that's involved with the solid. So the net ionic equation here is that sulfate is combining with silver to give us silver sulfate. Okay, so hopefully you got that one. Next one, sodium carbonate reacting with HCl. Okay, so swap. This one you might not have gotten, but let's go over it. So notice the products here. So we start with sodium carbonate, combine it with HCl, and you might have predicted this. So you might have predicted H2CO3 plus Na Cl. And you're not completely wrong. That's the first step. The problem is that this H2CO3 is unstable. So H2CO3 in the presence of an acid breaks down to give me CO2 and H2O. Okay, so if you see something like H2CO3, H2SO4, something like that, it's actually an unstable product. Okay, so it's actually going to break down into CO2 and into water. Okay, so that one is a little bit of a trick. Okay, so if you predicted these products, you're not on the wrong track. You just have to then recognize that this is an unstable product. Okay, so it has to be broken down into CO2 and into water. So that's why you end up here with CO2 gas, aqueous NaCl, and aqueous, of course, liquid water. Okay, so your complete ionic, again, just break everything into ions that can be. So notice this time, the only thing that can't be broken into ions is our gas. Okay, so if you were to ask the driving force for this reaction, this would be your driving force. Okay, and if I remove my spectator, sodium, carbonate I can't remove, H plus I can't remove, but I can remove chloride and chloride. So my net ionic, I have carbonate combining with H plus to give me CO2 and water. Okay, so again, if you predicted this, you're on the right track. Then it's just having to recognize that it's unstable and so that it breaks down. Okay, number 3. Okay, so swap nickel and magnesium. Predict your products. Check your solubility. Here we see that nickel 2 hydroxide is our soluble product, or insoluble product, excuse me. So that's our driving force. That's our molecular. Break everything into ions. Eliminate any spectator ions, and that's our net ionic equation. Okay, for 4, we have lithium phosphate reacting with calcium chloride. Okay, swap our cations. Look for our insoluble product. Here, this is this calcium phosphate. So that's your molecular. Complete ionic, break everything into ions that can be. Eliminate the spectators to get your net ionic equation. Okay, so I think that's a good place to end this video. I think we're about at the 30-minute mark. So I'm trying to keep these around there now. So I'll go ahead and end this here. When we pick back up, we'll talk about acid-base reactions.